I hope you enjoyed that fourth challenge. Let's take a look at the solution. So here, we didn't have to load a data set. We have a pre-coded notebook with code that lets us fine-tune two models with LoRa. So the first thing you should note is that much of this code, again, is already coded for you, right? There are simply two exercises that you'd had to do. One is the data preprocessing code cell, and the second one is the PEFT training code cell. So I will walk through the notebook, and when we get to the exercise section, I will talk about what the solution looks like. So here, the first thing we do, as usual, is we have to install dependencies. Now you'll notice here that there's a comment out with a pip install transformers, datasets, evaluate, accelerate, PEFT. Well, that is a shortcut to use rather than having to code each one of these. But what I've done is I've put them here so that you can actually understand what each one of these is doing. But feel free to uncomment this out and, of course, remove these if you need it. So, exercise number 1, dataset preprocessing. You had to define the model name. And you define the model name, Roberta _model_name. And this is the pre-trained errors fixed transformer using the Roberta base model. You also had to initialize a variable called modified base. And this is a modified version of the Roberta base model. And then you also had to initialize a variable called base model. And then you had to load the data set. And then you had to initialize a tokenizer using the base Roberta model. That was here. And then you had to define a preprocessing function. And this tokenizes the text data, truncating and padding sequences. And then you had to apply preprocessing to the entire data set in batches, removing the text column. And this is standard machine learning best practices. We're splitting the tokenized data set into train, evaluation, and test data sets. And here we're extracting the number of classes and their names. And here we're just printing those out. And then here we're creating an ID2 label mapping, and we will need this for our classifier. So we can classify whether a news article from our data set is either sports, entertainment, or business, for example. And then we have a data collator that we have to tokenize, and that returns a PyTorch tensor. And that's ran, and so just scrolling down here, and then there's training. And so here, the notebook trains two models, one using LoRa and the other with full fine-tuning. And these are the concepts that we talked about in the chapter. So with the LoRa training times and number of training parameters can be, with any model training time, it's going to be long, depending on many different factors, whether you are using CPUs or GPUs or TPUs, the amount of data you're bringing in, the type of data. But here you're simply going to just define the training arguments for the model training. And this is standard boilerplate code, if you will. And then down here, you're going to define a function to create a trainer object for model training. And you're going to create the object with the specified arguments, model equals model. And again, this is standard boilerplate trainer function code for creating a trainer object. So then you create a trainer object for full fine-tuning of the model, and that's here. And then we start training the model, and that's here. So the model is being trained, and you can see there's different steps, the training loss and the validation loss. Again, typical machine learning loss type of data that you would see. And then here we are going to actually do the parameter efficient fine-tuning training with LoRa. So here is where you had to create a model for sequence classification based on a pre-trained model, and that's what is here. And here you're configuring the LoRa parameters for PEFT, You noticed here that you have a few hyperparameters that you can modify, like the dropout rate and also the learning rate. And here you're applying LoRa parameters to the model to create the PEFT model. And then here you're going to simply print the information about the PEFT model's trainable parameters. And here you are obtaining a trainer object for LoRa fine-tuning. And then here you're initiating the training process for the PEFT model using LoRa fine-tuning. And then, so now we're going to be training this one. And again, standard machine learning training iterations table, if you will, the steps, the loss, the validation loss. And then we're going to save the models. Performing inference was not one of our exercises, but I think it's really worthwhile to take a look at the code. And you've noticed as I'm going through here that there are comments everywhere. And this is to help you really see what each line item is doing. So here we have a function that is going to tokenize the input text, truncate it if needed, pad sequences, and convert it to PyTorch tensors. And we're passing the tokenized input through the inference model to get predictions. So here they're going to then print the class of prediction and the label of prediction, and the text as well. So we're asking the model now to classify these two different sentences here and here. One has the word hospital, so something maybe health related, and then here this as Wall Street, so something perhaps maybe business related. And the class 1 label is sports, in terms of this person probably being left in the hospital and participating in some kind of sports. And then this label here in terms of Wall Street was business. And this is how these two different statements were classified. And this next section is just to measure the improvement of the training process, where you take a look at how the trained models perform against the untrained one. And this is the code that does that. And when everything is done, this is your final 3 cells. You'll have the evaluation of the non-fine-tuned model. You have the evaluation of the PEFT fine-tuned model and the fully fine-tuned model. And you can see they're pretty close here, 0.927 in terms of accuracy for the PEFT fine-tuned model, and then 0.946. And then, of course, here, the accuracy here on the non-fine-tuned model is 0.248 in terms of accuracy.